HLA, Horticulture and Landscape Architecture, that's HLA, /sites, SITES, /CEA. CEA stands for Controlled Environment Agriculture, okay. Everything, greenhouses, vertical farms, everything is under that controlled environment agriculture. But the reason why I want to show is this is my lab website. This is my website at Purdue University. And if you go here, you see there are a lot of other tabs, right? So the most important thing is I want you to click on the extension link, and then you see extension programs, publications, presentations, and few other things. But if you click on extension presentations, I hope it will open. This is one of the greenhouses where we do research. But if you go down here, you see here, these are all free presentations that you can download. Okay, this is about greenhouse production, you know, construction, transplant production, temperature management, heating, cooling, nutrition, light energy, smart sensors, water management. You can also look at floriculture crop production. There are lots and stuff about hydroponics, all of that. So if you click on each of them, for example, hydroponics 101, if you click on that, it will open a PowerPoint or a PDF file that you can freely download, okay? And it's all free source it's taking a little longer here to open, but it'll open eventually, okay? So this is an additional resource for you. Even after the program is over, yeah, you can see the presentation shows up, but you can download that. However, it's showing in a different format here because of the screen setup display, but you can download those PDF files. They're free, no cost involved, but that would be additional information for you. When you're done with this course, it's not the end of it. You can always go back and download this and use this information, okay? So that's what I want to let you know, okay? So let's go back to home now, and we'll start our, I'm learning this, so it's good. Now I'm going to go to USB drive and to Gyan. So today I'm going to use some of the things that I prepared. Lecture 110, lecture 2, it's difficult, right? I want to do lecture 3, which will be somewhere down here, right here, okay? Hopefully it'll open up, because it's much easier and the screen is bigger, and we can actually, how do I, it's getting really difficult. So I'm going to bring them. Just give me a second. I want this to expand. Can somebody help me? नहीं, what I'm trying to do is इसको single slide को बड़ा. That way, play on current slide. Okay. Okay, and then the way I move it is it this, right? Okay. Just like, but ये काम नहीं करेगा? हाथ से करना पड़ेगा. ठीक है. कोई problem नहीं. Okay. Thank you. We'll wait for her. So just before she comes, yesterday you learned about some basics of lights, right? Basic things like what is intensity, what is irradiance, the energy piece. We learned about daily light integral. We learned about light composition, why it is important. The colors of light, red, green, and blue, how they are important, how they affect photosynthesis, plant growth. Then we started learning about, how photoperiodism affects flowering, right? And then towards then we talked about, what else you can do with the light composition. You can increase the nutritional quality, you can, reduce the bacterial infestation on plants with certain particular energy rich wavelengths. So that's all basic stuff. The fundamental thing that you need to know when you try to apply these concepts, those fundamentals will really help you, and that's the reason why we went over that yesterday. Today's topic on light is applied. Yeah, go ahead, please. Yeah.
Sir, yesterday we talked about how UV irradiation can help in overcoming the stress of E. coli and other bacteria. Can it be used to other disease causal organisms also, or something of little bigger size? Or
yeah. So the question she's asking, I'm going to just explain a little more. So So the bacteria like E. coli, Salmonella, and Listeria, they are pathogenic to human beings. So they are human pathogens. They don't do anything to plants. Plants are like alternate hosts for them. The plants provide a space where they can survive, multiply, and grow, right? They don't do any harm to the plants. But then there are some pathogens that affect plants, right? Disease causing pathogens, fungi, bacteria. And can UV light be used to reduce the infestation of those pathogens? I did not do any research on that, but I'm going to make a guess here and give you an answer. Those pathogens that affect plants are more internalized, systematic, and they're inside the tissue. They're growing inside. So when you are exposing plants to UV light, the UV light may not penetrate deeper into the leaf tissue. It's probably right on the surface or maybe a little bit microns into the leaf. So that may not even get to those pathogens which are kind of inside the plant tissue. So therefore you may not get a good control with this UV light. If you use too much of UV light, you may be killing the plant rather than killing the pathogen. So that might I hope that helps you, but that's what in my opinion and best guess I can make. So it's probably not the best way to control plant pathogens. It's probably best to control those surface living bacteria that are just there, and then when you eat the plants, if their foliage or fruits or leafy greens, they multiply inside our stomach and cause problems. So for them, yes, UV can be a potential issue. Okay, so any other questions from yesterday before we move on to topic today? Any other questions? Was there anything confusing? Some concepts not clear from yesterday? All good then? Okay. All right, let's move on to today's topic. So today's topic on light is more on applied side. How can we use this light? What are the different types of artificial lights? Okay, things like that. I just put this picture again. You saw this picture from first class. So this carbon arc lamps, the halogen lamps, high pressure sodium, and different types of LEDs. These are all. But then we are more looking at this high pressure sodium lamps over here and these LEDs in the commercial greenhouse industry. These are just historical stuff. Okay. All right. So here is a picture, and I think you saw this picture yesterday, just kind of showing the importance of light. But I put a table here, okay, and you can see what's that beeping sound? वो आप वो सिस्टम का है या नहीं? ओके बीपिंग साउंड आ रहा है, आप जरा देख सकते हैं क्या है? गुड मॉर्निंग. So while they take a look at it, I think he might. But I want you to look at this table. So on this table, I put different categories of plants. You can see seedlings, tiny seedlings, leafy greens, annual flowers, shade plants, vegetables like tomatoes, peppers, eggplants. Eggplants is brinjal. Okay, in the US, eggplants are called brinjal. Brinjals are called eggplants. Okay, strawberries, fruits and things like that. And I put some numbers on the right side. Okay, but I want you to first focus on the units. What are those units? Moles per meter square per day. Remember moles per meter square per day?
Is this working properly?
Yes, now it is doing fine. But if you are available for us in case if there is a problem, I'll immediately.
You can use this pen drive.
For
Sir, your all the lecture in this pen drive. In any case, if this is not working,
uh-huh.
you can use this.
Yeah, I have a USB drive here, same as this, right? Okay, I'll just leave it here just in case. Okay, so continuing. So now take a look at this table. Moles per meter square per day. That is the amount of light you should be providing for these different categories of plants. This is the minimum requirement. Okay, this information is based on research. Okay, so you may be living in an area where people probably don't use lighting at all, but if you don't have this much light available, then you have to add artificial light. As you go northern latitudes, I'm guessing that even this region and further up north, the amount of light that you receive during winter goes down. Now sometimes the light may not be low in winters, but There could be days when it is cloudy, okay, several days, 4, 5, 6 days of cloudy weather. When the clouds are there, the amount of light that gets into the greenhouse significantly goes down. So let's say you are growing seedlings, okay, and you want the seedlings to be nice, compact, healthy, and green. And the seedlings are generally there for 3-4 weeks. After the fourth week, you normally transplant them, right? But out of that 4 weeks, let's say there was a week of cloudy weather. There is less light going through. And if the light levels are even below this, you have to apply artificial light, supplemental lighting. Okay. Same goes with other crops. Leafy greens, about 10 to 12 annual flowers. Flowers would be like, what type of annual flowers do you grow? Marigolds here, right? Zinnias, cosmas, petunias, begonias. These are all annual seedlings. Um, that is a big industry in the United States. We call them as bedding plants. Bedding plants, because what they do is they grow these seedlings, and when they flower, they look like a flower bed, a big flower bed. So they're very popular there. And so for them, at least you need to provide 10 moles. But the things that are more important, 10 to 15 moles. But shade plants, these are the indoor plants, right? We grow palms or Dieffenbachias and aglaonemas, monsteras, philodendrons in our homes. They require less light, and so about 5 to 10 is enough. But look at these tomatoes, the peppers, and brinjal. If you are growing them in a greenhouse, you need at least 20 moles. Okay. Now, that number is something you can use as a guideline, right? You need a sensor to know how much light you are getting. Without the sensor, these numbers mean nothing. So the important thing is you have to invest in a light sensor if you have a greenhouse. There is no escape from that. You may at least have one good light sensor in the middle of the greenhouse. If you can't connect it to a data logger and continuously monitor the numbers, at least have a handheld unit and periodically measure the intensity. And if the intensity values are lower than that, you may have to turn on artificial lights. Otherwise, you won't get quality. Otherwise, you won't get the yields that are desirable. Okay. Strawberry plants like strawberries is becoming very popular in greenhouses. It's a very profitable crop if you can do it very well. The reason is strawberries are only grown in some regions in the country and only during certain times of the year. But if you have a greenhouse, you can grow strawberries throughout the year. And I probably will talk a little bit more later on. The strawberries that you get outside in the field, they are called June bearers. Now they come fruiting in the months of May and June, but not after that. But if you are trying to grow strawberries in a greenhouse, you should not grow June bearers because they won't fruit throughout the year. In the greenhouse, you have to grow what we call day neutral strawberries. These strawberries are smaller in size, not like the big June bearers, but they come to fruiting in flushes throughout the year. So each flush is approximately, I would say, month and a half, and then the vegetative growth, and then flowering, and then fruits, and then vegetative growth, flowering, and fruits. So you get 5 to 6 fruiting cycles in a year throughout the year, so you can produce strawberries. So during the months where there is no strawberry available outside, for example, in the months of January, February, March, the strawberries are just starting to bloom around March, right? There is no strawberry, but if you can produce strawberries in greenhouse, you get a higher price for that, right? Even during the months of September, October, November, there is no strawberry from the field. So during the months you can probably produce in the greenhouse, but the strawberry is a difficult crop to grow. The most important thing for strawberry is nighttime temperatures. The nighttime temperature should be cooler, like 55 degrees Fahrenheit, or in the range of 12 to 15 degrees Celsius. If you can't maintain 12 to 15 degrees Celsius, strawberry fruits won't grow in size. And later on, I'll show you this afternoon some examples how temperature affects strawberries, but they won't be even sweet. So, but if you are in a region like this, where in the months of August, September, October, the weather is going to get cooler, you have a great chance of actually producing good quality strawberries in a greenhouse here, simply because it's cooler compared to south, right? But we'll talk more about that. So this slide should give you a guideline, an approximate amount of light these plants. You can provide this light through sunlight. which is the cheapest and best way, right? It's free sunlight. But if you don't get sufficient amount of light from sunlight, you have to add artificial lights. Okay, and that is what we're going to learn today. What are these artificial lights? How much they cost? What is the advantages and disadvantages? What are the different advantages, disadvantages? Which ones to choose versus others? Okay, and how do you increase, plant use of this light? Things like that. Okay, so that's the big topic for today. All right. All right. So why do you want artificial lighting? I think I kind of told you why we need artificial lighting, but I'm kind of summarizing. Artificial lighting provides additional light for photosynthesis during cloudy days or in winter months, right? When the light levels go down, the photosynthesis also goes down in plants. So the only way you maintain a higher rate of photosynthesis and continue that nice vegetative growth is by adding the artificial light. It also can be used to extend photo period. So yesterday we talked about photo period and its effects on flowering, right? So let's take chrysanthemums. Okay, um, if you want to propagate chrysanthemums, meaning you want to get cuttings, vegetative cuttings for chrysanthemums throughout the year. So let's say you are not in the business of producing chrysanthemum flowers or pots. Your job is a propagator. As a propagator, you want to produce cuttings, rooted cuttings of chrysanthemums. Okay, but these chrysanthemums will flower in winter under natural environmental conditions because there are short days. Remember the phytochrome thing that we talked yesterday? The PFR converts to PR and PR converts to PFR. During winter months, the night period is longer. So there will be very little of PFR in the plants. So that is a sort of like a signal for plants. So they start flowering. Once chrysanthemum flowers, you won't see a lot of vegetative growth. The main thing is now the flower. The plant size will get fixed. That is not suitable if you are a propagator, because you want more and more vegetative growth, so you can cut the tiny pieces of plants and you can propagate them. How do you maintain a vegetative growth in the plant? Vegetative growth in chrysanthemums during winter by adding artificial light. So the light may go down at 5:30, 6 o'clock in the evening, but you turn on the artificial light, it's like a longer day length for chrysanthemums. So they will still remain in vegetative growth. They won't flower. Even in winter, they won't flower. You continuously get more and more big plants. You can take cuttings, propagate them, and then sell them whenever they want. So it's an artificial way. So extend photo period. Okay. Some flowers, the chrysanthemum is a short day plant. Okay, but there are flowers that only bloom during long days. It's opposite of short days, long days. Okay, there are flowers that bloom only during long days. Such flowers, by simply extending photo period, you get better flowering. Okay, even with strawberries, strawberries, when they are growing strawberries, normally we plant strawberries in greenhouses during the months of August. And August and September, they're just growing bigger and getting bigger and bigger, and around September they start producing flowers, and then you get fruits in October, November, and then again they go down and then they start growing. But when they are growing vegetatively, when they are making the green mass, by adding more photo period, you can actually get a bigger size plants. Okay, that's another reason why you want to extend photo period. But the most important thing is crop quality. You can be growing tomatoes, peppers, leafy greens, flowers, anything. If these plants in greenhouse are exposed to low light, shaded conditions like cloudy days or in winter, the artificial lighting is the only way you could get good quality. Otherwise, the plants look sick, they won't fruit a lot. By adding this artificial light in northern latitudes, including this area and up into Kashmir, it is the only way you can get real good quality plants in winter is by adding supplemental light. We need light. We need artificial light. While they work on that, um, let me let me add a few more things. I don't want it to be dark. Um, is this common? Like you get power cuts often here? Is it? It's because it's summer and people are using air conditioning everywhere. Yeah, yeah. But in any case, while they start working on that, um, there are two major types of Vikramji. Should I continue talking because you are not probably? Shall I stop until the current power? Are you able to record then? Okay. Uh, so there are two major types of artificial lights. I'm using the word artificial light all the time, but in industry they use another word. They call it supplemental lighting. Okay. So both are same. Artificial lighting or supplemental lighting is same. Okay. Um, if you are trying to grow crops in a greenhouse and you are adding light, then it's probably better to call it a supplemental light, because what you are doing is you are supplementing to sunlight. Sunlight is already there. That's 80% of the total light plants get, but you are supplementing a little bit more. You are adding a little bit more to sunlight. That's why it's supplemental light. But let's say you are growing indoors, in a vertical farm. You have a building like this, and the building is not being used, and you wanted to grow some leafy greens. You want to grow saffron or some very expensive crops indoors, and you totally relied on, because it's inside a building, there is no sunlight coming into, so you are totally relied on artificial light. That's when you use the term artificial light. Okay, but they are very, very similar, but I want to give you the difference: supplemental lighting and artificial lighting. There is a lecture on vertical farming and indoor farming too, and I'll cover that in case if anybody is interested. Although it is not related to greenhouses, but still it is an important topic, so I've included a lecture on that later. So let's go back. So there are two major types of these artificial lights or supplemental lights. One is HPS, stands for high pressure sodium lamps. Okay. The other one are the LEDs, light emitting diodes, LEDs. These are the two major types. Since mid 80s or even earlier than that, the entire greenhouse industry was totally relying on high pressure sodium lamps, HPS lamps. In fact, if you notice that picture, that slide, on the right side there was a small greenhouse with yellow color lights inside. Those are high pressure sodium lamps. The sodium vapor is what is used inside the bulbs, and the sodium vapor releases that yellowish color light. Okay, that's why they are yellow in color. Okay. But when you get to LEDs, light emitting diodes, you can customize your lights to whatever you want, whatever color you want. You learned a lot yesterday about light composition and its importance on plant growth. Now, once you know that, oh, these are the colors of light we want, you can go and choose those LED bars with that specific recipe, light recipe that you want. The companies are able to manufacture. Okay, there we go. I hope that this will come back automatically. There it is. Now again, these LEDs are semiconductors. I don't want to go into the physics of that, but that is a very well established technology now. And I'm going to talk now about these two lights, supplemental lighting, major types of supplemental lighting. I want to tell you the advantages and disadvantages of both of them. Okay, both of them have some advantages and disadvantages, but knowing that is important. So we'll wait for a minute or less than that for this to open up. You don't have any um, power generator or something? Okay. Oh, this is generator. Okay. So it won't come on automatically? My USB. What has that? What happened to you? Oh, YouTube. Okay. Please wait 1 second, because last time I know you did something. Go to lectures, and I want to go to lecture 3, which is here, and you did something. Okay, go to play, and no, current page. Okay, and then just swipe. Comes up. There you go. Okay. So here, this is the slide where we were before, right? So we were talking about crop quality, right? Now there are two other benefits of artificial lighting. This is the sodium vapor lamp, yellow color lights, artificial lights put on top of the greenhouse. In addition to providing that light, there is also some heat coming from them because they are so much, they consume a lot of power. So some heat comes out. So in winter months, your heating requirement can go down. You don't have to add, heaters. Of course, you have to add heaters, but there is a little bit of benefit that comes from these high pressure sodium lamps in that they actually add some heat. So your overall heating requirement, artificial heating requirement, kind of goes down a little bit, not much, a little bit. But the most important thing I want to remember is this. Yeah, we are having artificial lights. It doesn't mean that they are as bright as sunlight. No, it's not possible. Most of them can only give you about 150 to 200 micromoles. Although I have a range here between 100 to 400, generally speaking, most of these artificial lights can only provide approximately 150 to 200 micromoles per meter square per second. Okay. The thing is, if you remember from yesterday's tutorials, you did DLI calculations, and I put supplemental lighting 150 or something during the night times. You see that number is constant for several hours. The reason is the light that they output is low intensity, but it's constant. Unlike sunlight, it goes up in the afternoon and comes down in the evening. The artificial light remains flat, but it's only 150 to 200 micromoles. That's all you can get from this. Okay, not too much. Okay. So here are some. So here is a tomato greenhouse. There is another greenhouse here. But these are high pressure sodium lamps. You can see that inside, completely yellowish in color. And these are the LED lights, and we'll talk about this. But what I want you to show is these two graphs. So yesterday I kind of showed you a graph like this. When we were talking about light composition, I showed you a graph where on the x-axis you had 400 to 700 nanometers, and I told you that you can measure the intensity of each nanometer, when you are looking at light composition. Such graphs are called spectral graphs. Okay, these are spectral graphs. Okay, you are looking at the spectrum of the light. So this is how the spectrum of high pressure sodium lamps are, and these are LEDs. But let's look at the spectrum again. Look at the x-axis. What is x-axis? Wavelength, right? PAR, photosynthetically active radiation, 400 to 700 nanometers. Okay, and then y-axis is, they're showing energy, but you can see the spectrum. I want you to tell me, and then you have some colors of light too here, but notice that with the high pressure sodium lamps, there is a very little of blue, right? Very little of blue here. There is also very little of red here, right? But what is the most significant color you're getting? The green and yellows. Green and yellow colors. And that's why they are yellowish in color. Okay? I will get back to that. Remember that, green and yellow. Now here are some LED lights. We have white LEDs, we have purple LEDs. Purple is blue plus red. Okay, that is purple. But here is a purple LED. What do you see here? Again, x-axis is wavelength, and y-axis is again the percentage of that particular energy. And then you can see a lot of it is coming from red and a small portion coming from blue. Okay, so here this spectrum is ideal for plants because chlorophyll absorbs the blue and the red bands. So if you provide plants with a lot of green and yellow color, which the chlorophyll absorbs but not as much, reflects a lot. So you are wasting light, right? A lot of light. Whereas here you are providing light that plants completely absorb and use. On one side you are buying artificial lights, that's money. Then you are paying for electricity, that's money. And all of that is to generate photons. And if you are generating a lot of green and yellow photons, of course, they are absorbed by plants, but they are not as efficient as red light in terms of photosynthesis and energy, right? So that is one of the major disadvantages of the HPS compared to LED lights. Okay, with the LEDs, here we customized. We went to the manufacturer. The manufacturers already know this because they saw the research, and what they're doing is, let's put a little bit of light, blue light, but let's put a lot of red light for plants. Okay. So that the spectral graphs, the spectral information is critical. You may have high intensity, like 500 micromoles with HPS lamps, but most of that is coming from greenish yellow bands. Okay, but on the other hand, here you have high spectrum, but most of that is red light. Really good for plants. Okay. All right. So some more information about HPS and LEDs. So this is how that HPS light fixture looks. Okay. This is what is hung up at the top of the greenhouse. This is how the LED bars. Some examples. Okay. But look at this graph. What is this graph telling you? Let's say you have this light fixture right here. Okay, you have light fixture here. I think it's continuously playing, and if I don't speak fast enough, it goes to the next slide immediately. But let's say you have a light fixture here with high pressure sodium lamps. You get the light. This is the orange bar, orange curve is the high pressure sodium lamp, and you are getting light kind of distributed in a much wider area with high pressure sodium lamps. So you put the lamp up there, you get illumination in a wider area. Okay, but compare that with LEDs. Most of the light for the LEDs is in a shorter region. Okay, that's the major difference. LEDs send light out in 120-degree angle from the fixture. They just come like at 120 degrees angle. They will illuminate a smaller area with brightness, whereas high pressure sodium lamps illuminate a much wider area. If you are illuminating a smaller area, what is the disadvantage of that? Can you think of it? So you have LED bar here and you're illuminating this much area. What does that mean? Well, think about,
So the number of
yes,
required will be
more, right? You need more LED bars, right? But you need a fewer of high pressure sodium lamps to illuminate the entire greenhouse. So let's say you have a 10 meters by 50 meters greenhouse. Okay, you probably can just buy 10 high pressure sodium lamps, put them along the length, and you get the entire greenhouse illuminated. Cheaper for you. But if you are going for LEDs, you need to buy a lot more of them. So in the previous slide, I showed you the advantage the LEDs have, but with the spectrum, you can customize the spectrum you want. You can get really good plant growth, everything, but then they are expensive. Also, look at the prices here. I put it in dollars. You can convert 90 rupees, approximately 87 rupees is a dollar. Okay, but just look at the almost 3 times more LED bars compared to high pressure sodium lamps. So they are expensive. LEDs are expensive compared to high pressure sodium lamps. High pressure sodium lamps are cheaper. You also get the benefit of wider light coverage, illumination. Therefore, you will need fewer number of lamps in a greenhouse. But the real problem is they don't provide the best light composition. Okay, that makes sense to all of you. That's what I explained here. But there is one major advantage of LEDs. So you probably have heard about LED lights, right? Nowadays, why do you use LEDs in your home? We have replaced halogen lights and all those things now with LED lights in our houses. Why do you want to use? What do you mean by efficient? Yeah, electricity bills are less, right? Energy costs are less. That is a major advantage. So I'll tell you why. These HPS lamps, they are between 400 watts to 1000 watts. Okay, meaning if you turn on these HPS lamps for 1 hour, let's say it's 1000 watt, okay, 1000 watt HPS light. You run that HPS light for 1 hour, that's 1 kilowatt hour. 1000 watts are consumed per hour. 1 kilowatt hour is 1 unit of electricity. So these are consuming 1 unit of electricity every hour. Every hour. 1 One fixture consumes 1 electrical unit every hour. On the other hand, LEDs are operated at 100 watts, 100 to 150 watts generally, meaning you have to run these LEDs for 10 hours to consume 1 unit of electricity. 10 times more efficient. So they generate a lot of light with less power. With 100 watts, they generate 250 to 300 micromoles, whereas these require almost 400 to 1000 watts to generate same amount of light. Yes, there is a benefit here. They are much wider in distribution. You will need fewer number of those HPS lights. They are also cheaper. But the problem with them is their spectrum is not ideal for plants and they consume a lot of electrical energy. So what the experience tells us is you may invest more on LEDs initially, but in a span of 10 years, you will recover the cost because you are paying less every month for electricity. That is the major benefit. So over time, the benefit shows up. And therefore, these LEDs are becoming very popular. There is one other thing I want to mention. These HPS lamps, those bulbs inside, I think their life is only 2 or 3 years. Afterwards, you have to replace the bulb. But the LEDs have a much longer life. 50,000 hours, 40,000 hours. A lot of, lifespan for them. So again, lot of benefits, pros and cons, negatives and positives of both lighting. And what type of lighting you want depends on your selection. If you have money to invest in LEDs, go for it because they're going to pay you over time in 10 years. But if you don't have money to invest in initial capital, then maybe HPS lamps are an alternative for you. Okay, those are the two major types of lights. Anywhere you go globally, these are the major two types of supplemental lighting in the greenhouses. But you need to know what are these LEDs and what are these HPS and why should I choose one over the other. Okay. Now let's talk a little bit more about LED lighting. Okay, so we talked about HPS and LED. We compared them. Now let's focus a little bit more on LEDs. You got two types of LEDs. Okay. Again, what are these graphs called? Spectral graphs, right? What is a spectral graph? On the x-axis you will find nanometers light, and for each nanometer, for example, if I'm interested in 440 nanometers, that's the amount of intensity. If I'm interested in, it's really touch sensitive, if I'm interested in 500 nanometers, that's the intensity. So I can look at the intensity of every nanometer wavelength. That's a spectral graph. You get this type of information from a sensor called spectroradiometer. Okay, spectroradiometer. It's a little bit expensive compared to quantum sensor. Quantum sensor is, I told you yesterday, $250 to $400 each sensor. And that sensor measures the total amount of photons, number of photons falling in a meter square area per second. That sensor does not tell you whether you have more of green versus blue or red photons. It's only going to tell you the total amount of photons falling in 1 unit area. But if you want to get to that level of light composition and want to know how much the blue light is there, how much the green and red are there, you have to buy a spectroradiometer. The spectroradiometer gives you graphs like this, where you can go and say, okay, from here to here is blue and I want to know the total of that, here to here is green, here to here is red, so I can add all those numbers and I can get what percentage of blue is there, what percentage of red is there, you can determine from that. Okay. So these are the two spectral graphs, and these spectral graphs tell you that there are two types of LEDs. Okay, these are called broad spectrum LEDs, meaning you have light in all wavelengths from 400 to 700, right? Compare this graph with this graph. What is the major difference? And is there any light in between? There is no light. There is no light. But here, continuous, broad band. It's broad. This is narrow band. Two colors, all colors. Broadband versus narrow band lighting. Okay. And the reason why you see these two is because the way these LEDs are manufactured. Most likely, if you see a bar like a broad brand LED like this, the way they manufacture this is they start with blue LEDs. Okay, blue. These blue LEDs were discovered in 1960s, and that was like a revolution. And that's the reason why the discoverers got Nobel Prize too. The blue LEDs have a lot of energy, right? You know, the blue photons have a lot of energy, right? Because of the wavelength is smaller. So they start with blue LEDs, and they add, you know, like your fluorescent lights, the tube lights that we have in our house. If you have seen, if you have broken any of the tube lights, inside you have a coating, right? White coating, you will see that. Like that, they put a coating, what we call phosphor conversion. It's called phosphor conversion. We use a material called phosphor, and they put that phosphor, what we call doping, that's what it's called, on top of these blue LEDs. And when they do that, the blue LED generates all other colors of light. You are getting green, yellow, orange, red light from the blue light. And that's the reason why, so this has got a big blue peak here, there's a blue LEDs here, but then all the other colors are because of that phosphor conversion. So you get a full, broad, full spectrum LED lights here. The reason why they do this type of this is very cheap to do like that. Blue LEDs are very cheap, and from a few blue LEDs, you can get a lot of other colors too by applying that coating, the doping on that. That is one model. That is one model. That is the most common one you will see. When you see a spectrum like this, you should almost immediately know, oh, okay, these are all based on blue LEDs. They are getting different other colors from blue. Okay, phosphor conversion. It's called phosphor conversion. The other model, these are more expensive. Here, there are two types of LEDs. What are those two types of LEDs? Red and blue. It's two separate. There is no phosphor, nothing there. You have red LEDs and you have blue LEDs. If you want 75% red light and 25% blue light, you put 75% red LEDs and 25% blue LEDs. That is expensive because you got to buy two separate types of LEDs. That's called narrowband. Okay, these are the two major types. You don't see often this in commercial applications because they're expensive, but if you're a researcher, probably this is one thing you might choose. Okay, all right. Let's say I want to make sure I did not, yeah. Okay, so now we know there are two types of LEDs. I want to talk about a little bit more about a couple of terms, very, very applied terms. If you are buying LED lights, you need to keep this information in mind. And one of them is called photon efficiency. Okay, it's a term which is used to categorize different LEDs. So you go to the market, you have a greenhouse, and you want to buy some LED lights. And you know, I want 250 micromoles intensity. You know that. What intensity is, you know that there's a number of photons falling. You also will ask for composition. You will find, okay, it's got less blue light, it's got a lot of red lights, all good. Okay. So these are all the different criteria, right? When you go and buy a product, you look for specification, right? If you're buying a refrigerator, you want to know how much energy it consumes, you know, how much cooling you get, how big it is, how small it is, you know, what color it is, all that. Just like that for LEDs also, you will look at these things. But there is one more thing you should pay attention to when you are buying LED lights. That is called the photon efficiency. Okay, it is defined as light generated, the amount of light, intensity of light, okay, micromoles per meter square per second, okay, or micromoles per second, light generated per unit of electricity. So you give light, right? You plug this into the wall and the electricity is going into the bar. For each unit, how much light is produced? The reason why you want to look at that is the higher the photon efficiency, you see the higher the numbers, 2, 2.4, 2.5, electricity cost is what? Look at this graph. So if you look at this graph, hello, if you look at this graph, on the x-axis, what do you have? You have photon efficiency. On the y-axis, you have electricity cost, how much you will pay. As the photon efficiency is increasing, right, what is happening to electricity costs? Increasing. So that is why it is so important. You want to buy LED bars which have at least 2.5 photon efficiency of 2.5 micromoles per joule. This is the amount of micromoles of light produced per unit of power, joules of energy. Okay, that number 2.5 is something I want you to remember. If you buy products that are of lower photon efficiencies, your energy costs are going up. Now look at the photon efficiency of HPS and LEDs. HPS is around 0.7 at best right here, 0.4 to 0.7. So you pay about 7.5 cents in this case, in US currency, 7.5 cents. But your LEDs are right here, 2.5. You're paying 1/3 of that cost. So in addition to knowing how much light that bar generates, what is the composition of light you are getting, you should also ask the manufacturer what is the photon efficiency of that. Okay, those three criteria are absolutely important while selecting an LED light: intensity of light, composition of light, and the photon efficiency. If photon efficiency should be higher than how much? 2.5. Composition wise, what do you want to ask?
Red one.
More red, about 10-15% blue, and a lot more of red light. A little bit of green is okay. Now, people want to definitely add green light. Although they know that green light is more reflected, they do want to add a little bit of green light. The reason is very simple. If you have just the blue and red LEDs, the overall color is purple color. I think I have a picture here somewhere. Let's see. Let's go back. Look at this. That's purple color. If your entire greenhouse is of that color, after some time, working in that greenhouse, your eyes will feel like, it's a little bit strained because it's not white color. It's purple color. But the most disadvantage with the purple color is if there are some problems on the leaves, like, diseases, you can't clearly see them in that purple color. Whereas if the color is white like this, which we are all accustomed to, you can clearly see the plants, pathogen problems, disease problems, insect problems. So that's why what people do is they will keep 10-15% blue. They will also add a little bit of green, 15-20% sometimes, and then a lot of red light, 65%. When you add blue, green, and red, the color you see is more white in color. Three colors, red, green, and blue, you combine them, you get white color. So just for observation's sake, they add a little bit of green light. But there is also some research that shows that green light may have a potential value after it is absorbed, things like that. But for this class, it's not that important. But remember that purple color, white color LEDs, okay? So this white color LED, so I'm going to go back to the previous spectral graph and I'm going to ask you, look at this white color LED and look at that purple color LED. Now let's go back to why is this not growing? I think we need to ask them. Okay. I think you should sit here all the time. There you. What did you do? You just did that? Okay, this is my finger maybe. Okay, look at these two graphs. Which one is white color? Which one is purple color? Out of these two LEDs.
First one is white.
This one is white.
Second one is purple.
Yeah, why do you think this is white? Can anyone, not you, but anyone else? Why do you think this is white? Because you have green, you have what else? Blue?
We have
All the three colors. That's why the broad spectrum LEDs are generally white. This color is purple. You got just two colors, purple, okay? So you can look at the spectrum and tell what color it's going to be. Okay, we did this. So here is another term. So we talked about photon efficiency, right? Photon efficiency is something you should ask the manufacturer. But that photon efficiency is not in our hands. It is in engineering term, right? It is what the manufacturers can increase, right? They have to come up with really good efficient LEDs, really good semiconductors. It is not something as greenhouse growers or greenhouse researchers we can change. It is already built into the fixture. We can't do anything after we buy it. But then after photon efficiency, if you want to really use the light in the most efficient way, there is another term called light use efficiency. Okay? And I want to explain that using these three graphs. The first one is, again, keep in mind why we are interested in this, because you are adding light, and that light, for that light you paid for the light, fixed cost, and you are paying every month electricity cost. So it is expensive. Every photon that comes from that artificial light, ideally you want that photon to be used by the plants. If you have plants here and the light is falling here, it's all wasted. You are paying for that, right? So what I'm trying to tell you now is, how do you maximize the use of that artificial light? The number one thing is, look at these two pictures. This and this, okay, just these two pictures. In which picture, with the left or right one, you will see more light being used? This one or this one? This. Why?
The largest surface area for light.
The leaves are intercepting, right? So the number one thing you want to do is, you want to make sure that the light is not being wasted, and most of the light is being used by the plants. So what we normally do in hydroponics or any other production is, when the plants are smaller, put them close by. So all the light falls on seedlings, and as the plants get bigger, space them out if possible. Okay. So number one factor is light interception by the leaves. The more light intercepted, the more efficient it is, right? So you don't want to waste the light. So especially when plants are small, a lot of light can get wasted, because seedlings are tiny and everything light is falling outside of the seedlings and it's all getting wasted. So you want to at least keep them close by. Remember yesterday I talked about far red light, little bit about far red light, and I told you when you give a little bit of far red light, the leaves expand. Initially they give far red light for a week or so, and then afterwards they change to different light. You know the reason why they want the leaves to expand is that when the leaves expand, they intercept more light. All of that light is not, most of that light is used, less is wasted. Okay.
Image on the right one, the light is not very uniform. As we can see on a certain part of the leaf, there is a lot of light.
Yeah.
And on certain part, it is not that very much. But on the case of the left, the light is very uniform.
Yeah.
Yesterday, you told if the light is not very uniform, it will also have a negative effect on the
Sure,
plant.
sure. But this is just an example.
I think the left one is more efficient in that.
But I don't have the numbers to calculate, but I can with certainty tell you that there is a lot more light being wasted here than this one. But again, you know that bright spot, it's not artificial light, it's coming from sunlight. It's a picture from greenhouse. I just put it as an example for you. Okay, if you are growing these plants inside under supplemental lighting, you won't see that type of patches, but this is just sunlight. This is an example to tell you why that leaf area, why that canopy coverage, the leaf area, is so important for interception. That's all. Okay, nothing more than that. Okay, but again, remember, the quicker the leaves grow, the faster the leaves grow, the more efficiency you get from artificial light, because all those leaves are intercepting light and using those photons. The slower the plant grows, the more wastage it is for you. And so when you have smaller plants which are growing slower, you may want to keep them closer. There is another thing you can do with LED lights. Good, because he's asking questions and I'm getting more answers for you. Okay, so please ask more questions. With the LED bars, I forgot to mention one important characteristics. The LED bars, I don't know whether you experience this. You can touch the LED light and it will be kind of cool or warm to touch. It's not going to burn your fingers or light. If I touch the high pressure sodium lamps, I get a big burn in my. The LEDs are cool to touch. Because they are cool to touch, what you can do is you can put these LED bars close to the plants. What happens when I put, let's say you have a small plant, if I put the LED bar here, the light is going like this. A lot of light is getting wasted here when the plant is right here. But if I bring the bar down closer, the light is actually falling straight on the plant and the plants are getting a lot more light. So that advantage is there with LEDs. You can lower them to avoid such problems. You can either put more plants in that area, small plants, or you can bring the LEDs down. Okay, that's one advantage. You can't do that with high pressure sodium lamps. You bring the high pressure sodium lamps should be at least 8 feet from the plants. If you bring them closer, they can scorch the plants. The plants can get pretty hot. Okay, another disadvantage with HPS. But the LEDs, you can do that. That's another way you can increase light diffusion. So the number one factor is light interception by plants. You always should try to maximize that. How do you maximize? Either put lots and lots of plants together on the light, or bring the light bars like LEDs down closer so less light is wasted. That's how you maximize light interception. The second factor is light absorption by plants. So the light falls on the leaves. That's called interception. Then that intercepted light is absorbed. How is light absorbed by plants? Pigments, right? Chlorophyll, xanthophylls, anthocyanins, all these pigments absorb light. So that would be the light absorption, and you see here there is light absorption. So here I'm showing you the different pigments and where they absorb. Look for the chlorophyll. Chlorophyll is in either a solid green line or a dashed green line. Okay, chlorophyll is in green color pigment. So you see where the maximum chlorophyll absorption is. It's happening in the blue band, and it's also happening in the red band. So if I'm using a high pressure sodium lamp which has got a peak in this area where chlorophyll doesn't absorb, so all of that light, although the leaves are wider, let's say you have a wide plant, the high pressure sodium light is falling on it, but there are not many pigments that absorb that yellowish or greenish bands there. So of course the yellow and greens are also absorbed, but a little bit. You see that absorption of chlorophyll is very little in that range, but absorption of chlorophyll peaks in the blue and in the red band. So you want to really customize your light composition. So that's the second factor. So light interception, then light absorption. If you take care of these two things, then also that composition, the third thing is light quantum efficiency or photosynthetic efficiency. That is that. I've already shown you that. So if you take care of these three things, maximize light interception, maximize light absorption, and maximize photosynthetic efficiency by altering composition, you get the maximum light use efficiency. This is in our hands. Photon efficiency is done by the manufacturer. It's not in our hands. It's engineers who manufacture lights. So you want to make sure you buy a fixture which has got 2.5 at least photon efficiency. But after you buy lights, you have to do some cultural practices, or you have to do some selection such that light interception, light absorption, and photosynthesis are maximized. When you take care of these things, whatever dollars or rupees or money you put on these artificial lights, you get the maximum return from them. Otherwise, you will invest a lot and you waste a lot of money. Okay, I think that's the. If I'm not mistaken, is there any other? Oh yeah, I believe this is the last slide. This is just some other additional terminology. I want to talk about two things which you will commonly see if you are reading some papers. There are two terms called PPF and PPFD. Okay, two things, and I'm going to expand that for you. PPF stands for photosynthetic photon flux. Okay, photosynthetic photon flux. PPFD stands for photosynthetic photon flux density. Two things, and I'll explain them in a minute. Just remember the terms: photosynthetic photon flux and photosynthetic photon flux density. Okay. Now, can anybody tell me the units of light intensity? Units of light intensity per second, right? There is per meter square there in that unit. When you have per meter square, that is called photosynthetic photon flux density, PPFD. Okay. Now, when you are buying light from a company, the company won't give you PPFD values. They will give you PPF values. What they are doing is they take the lights in their company about approximately 2 feet below the light, they will measure the light intensity. Just about 2 feet below. And they will give you values in micromoles per second, no meter square. Just the flux of the light. Okay. So why is this important? So you may, let's say you look at, go to a company and the company says, oh, our light gives you a photosynthetic photon flux of 250 micromoles per second. Oh, it looks very good. So I buy that. And I put it up here, and then I come and bring a quantum sensor and I measure the light. I see maybe 120, not 250. The reason why that is happening is shown in this picture. Look at this one. They are measuring the intensity of ppf right at that level, whereas your plants are down here. By the time that light passed from that to this, the intensity has gone down. Okay, so always companies sell based on the flux, higher numbers. They only measure about 2 feet below the light, because they don't know at what height your plants are in your greenhouse. You may put them close, you may put them far away. So they don't know about that. What they are doing is, at a standard height, 2 feet below the light, this is the amount of light you get. You should not always rely on that, because you may put the lights above or below, you don't know, it's your scenario. What you are really worried about is how much light is there on top of the plants, not 2 feet below the light fixture. What is important is what is the light above the plants, right above the top of the plants. And you want that number to be close to 250. If you want to get 250 micromoles here, the ppf should be at least 400 to 450 micromoles. Okay, so remember those two terms, ppf and ppfd. What you are interested is in ppfd, which is the intensity, micromoles per meter square per second, whereas the companies sell as micromoles per second. They don't normalize for meter square area. They are giving you some numbers right below the lamp, standard value. Okay, remember the difference. So a lot of things, right? This chapter is all about, lights, artificial lights. Hello. And what you can do when you, what are the things you should keep in your mind when you are buying artificial lights? You have to look for light intensity values. You want the ppfd numbers close to 250 micromoles. You want to look for optimum quality or composition. You want to maximize the colors that enhance photosynthesis, the blues and the reds. And then you also want to look for the light that has highest photon efficiency, meaning your electricity costs are going to be less. If you keep these things in mind and look for lights, because investment in lights can be big in a greenhouse. Okay, and you want to make sure that whatever money, wherever money you're putting in, that money is properly done, the investment is properly done. You don't want to invest in some lighting with a lot of money and then figure out that, oh gosh, this is not the right type of light I want for my plants. This is too much of wastage, it consumes a lot of electricity, it doesn't have proper composition spectrum we need for plants. So knowing these things is critical, and that's the intention of this chapter. Very, very applied. Okay. The earlier chapter talked about what is intensity, what is composition, all that stuff. But then now we are applying those terms in this chapter, and we are trying to identify the best lighting. It's going to be LED lights or high pressure sodium lamps. Both have got benefits, right? Who can tell me the benefits of high pressure sodium lamps? Benefits of high pressure sodium lamps. Go ahead.
So the first benefit is that it radiates a greater area
Illumination is wider.
illumination is
Mhm.
wider as compared to the LEDs, and also the number of high pressure sodium lamps will be required, will be lesser as compared to the LEDs.
Correct.
For radiating the same amount of area.
Correct. And what is the benefit of less number? Less investment, less cost. So your investment is less, light coverage is more. But what are the disadvantages then?
High electricity.
High electricity, so you pay more for electricity costs. You may get a little benefit for the temperature, so it's actually added to the benefit side, not on the disadvantage side. But
Getting the favorable light bands that we
right,
require.
composition wise, right? Composition wise, you won't get that, right? But still, because of the cost is less, still high pressure sodium lamps kind of dominate the industry. People are worried about investment because LED investment is big. like I said, you have to wait for 10 years to start seeing the benefits of, less electrical energy costs. So investment can be big for some people, and so they still want to invest in hypersodium lamps. But this chapter should give you enough knowledge to choose what you want, right? What you choose is up to you, right? What you choose is up to the grower, depending on their resources and how much they can invest. But at least you have now the knowledge. Oh, I want to choose this versus this because of ABC reasons, right? That's what it is about. Okay, I think that's the last slide. Let's see if there is one more slide. No. Yeah, that's the last slide. Any questions on this chapter? I don't know what the time is, and this is not turning on today. Is it 10:30? 10:45. So we went over time. Okay. Well, we'll take a quick break, maybe. I don't know, maybe 10-minute break. Okay. Well, give me back 5 minutes. Okay. Instead of 15, take 10-minute break and come back in 10, and we'll start the temperature chapter. So, okay, it'll be very interesting. 10-minute break.